You're welcome to techtalks.com, which is a center of technology, education, and business. We are proceeding with organic chemistry, and we are looking at isomerism of organic compounds, but we have now reached position isomerism. We have now reached position isomerism. Now, position isomerism is the existence of different compounds with the same molecular formula and functional group but differ in the position taken by the functional Yes, that's the meaning of position isomerism. These are two different compounds completely with the same molecular formula, same functional group, but now the functional group is at different positions of the carbon skeleton. The first isomer could have position on carbon 1, when the second isomer has position or the functional group on carbon 2. Those two become very different compounds. However, chemical properties will be the same because chemical properties depend on the functional group. Functional group is the same. It is the difference in the positions taken by the functional groups that cause them to be different. That is position isomerism. Now, this position isomerism, we can look at a few examples here really. A few examples, we can look at C6. Now, let me look at the first example on alkyne. And remember I said alkynes have a general formula CnH2n-2. C6H this is 10 H10. Now, looking at the first isomer, which could be CH3, CH2, CH2, those are 4, these are now 5 and 6. Those are 1, 2, 3, 4, 5, 6 carbons. Then hydrogens, these are 6, 9, 10. So this one we call it hex 1 ion. So this 1 stands for the position taken by the functional group. Now, suppose this position moves from carbon 1 to carbon 2, that becomes a different isomer. For example, CH3, CH2, CH2C, like that one. So the difference between the two, you can see the structure is the same. All of them are horizontal and the horizontal setup is having 6 carbon atoms in each. But this one has a triple bond on the second carbon, this one has a triple bond on the first carbon. So this becomes a hex to ine. So the two are different by the virtue of the position taken by the functional group. Yeah, that is the position isomerism. Now, suppose this position of functional group now changes from this second carbon to the third carbon. Take an example, we have CH3, CH, we get hex 3 ine. 3 means the position taken by the functional group. Whether you come from right towards left, this is a third carbon. Even when you come from left towards right, this becomes a third carbon. But when you're looking at this, suppose somebody comes from left towards right, this is going to be the fourth carbon. But remember we said position taken must be the lowest. So somebody is coming from the left, looks at position 4. Somebody moving from right looks at position 2. Then this becomes the right isomer. So that is one of the examples of position isomerism. One of the examples of really position isomerism. Now, let me look at another example, but this time from an alcohol. I'm looking at an example of position isomerism, and this time from an alcohol. Now, suppose I'm having C5, this is supposed to be H12, then O. H12, then O. Now, writing the structure of this, the first isomer would be CH3, CH2, 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 those are 4, then CH, then OH. Count number of carbon atoms, 1, 2, 3, 4, 5. Then hydrogens, these are 8, 11, 12. So that is the first isomer of that given molecule. So we can name it as pentan, then you put the position of functional group, then all. That becomes pentan 1-all. So now we are going to keep changing positions of the OH until we can't form any other isomer. So for example, if I change position of this from carbon 1 to this carbon 2, I'll be able to have CH3, CH2, CH2, CH. Then I put my OH here, then I have CH3. So since this is now in position 2, then it still becomes pentan 2-all. So this isomer is different from the other one by the virtue of the position of the functional group. That now the functional group here is on carbon 2, while the functional group here is on carbon 1. Is really on carbon 1. Now I can also change this position from this carbon to this carbon, so that I will obtain CH3, CH2, CH, CH2, then CH3. So when you look at this isomer, counting from right to left, this is from carbon 3, this carbon 2, this carbon 1. So therefore I'll say this is pentan 3, then all. So the three isomers are different by the virtue of the position of their functional groups. But don't forget about meaning of positional isomerism. We say positional isomerism is the existence of different compounds with the same molecular formula, same functional group, all of them have OH, but differ in the position taken by the functional group. If molecular formula is the same, functional group is the same, all have OH, but just the position is taken by the functional groups differing, then the isomers we are obtaining are what we call position isomers.